Okay, so today we're gonna switch gear a little bit and talk about how you deal with I/O, right? And in general, also the concept of streams, which is something uh, that plays actually a really important part in modern day computing. And in terms of functional programming, we it might be a good idea to actually kind of solidify how we should interface with these kind of like infinite sequence of things, right? So let me first begin by asking this question. Uh, let's say I give you an assignment. When do you actually start working on it? This is a question not about critique. It's a question. It's an honest question for me. I'm gonna ask you. Naturally, when you actually start working on it, and it's okay to say whatever number. Oh, when they're free, okay. So how many people here take a quick look at the assignment and kind of like think about how long I would take to finish the assignment and then allocate that much time right before it's due for that? Yeah, so you have like number of days before it's due, right? So if I release the assignment, which by the way, assignment 3 is out, and don't cry. Uh, so so basically many people, including myself, right? I would do it in a lazy way, in a sense that I won't start until I know I must start, otherwise I'll miss the deadline. At least that's me back in the day, right? These days I don't even know. It's like it becomes like earliest deadline first. There's so many deadlines in my life right now. And in the past, like I don't know, N years before this. But this is something that human do, right? So and we call this procrastination. Everyone knows about the word, right? How many people procrastinate? I do. I mean, everyone does. And computer can also procrastinate too, right? Because sometimes it's a lot of like computation that you have to do. So you don't have to do it now. Computer will say, "Hey, I'm gonna do it later. I'll make sure the time I have right now is dedicated for something else." Right? So let me ask you another question. So let's say I procrastinate or you procrastinate. How I- how am I going to use my time that I gain from my procrastination? Can anyone entertain me with like some of the things that you do uh, after you procrastinate? Okay, I see silence, so I assume that it's kind of an awkward question. So let me start with uh, I guess one of the quote unquote right question is you have many homeworks, right? So you procrastinate one so that you can finish the other that has earlier deadline. That's a totally legit example. A more honest example would be back in the day when I was a student, sometimes I procrastinate so I can play games for a bit, right? To relax, right? Uh, in computer and basically the way computer works in general is you can procrastinate too so that you can use the time that you gain for running something else, right? Uh, you only have to evaluate things that you know you need. If you know that, hey, I'm gonna need this in the future in the next 5 days, you don't have to run it now. It depends, right? If you run it now versus run it in the next 3 days versus run it right away, right before the deadline, in many cases, it doesn't matter when you run it. It's just a matter of like you just have to finish it at some point in time, right? So sometimes this can lead to actually more efficiency, right? A better use of your time. If you're not running it right now, you can turn the power off for a little bit, like lower the frequency, save something, right? So we evaluated using the concept of stream. So what does stream mean? In English, by the way, I'm asking you, what does stream when you see that word in English? What does it mean? It's perfect. It's a constant flow of something, right? So in this case, we are talking about data, right? So it's a flow of data. Can someone give me an example of a flow of like what would I consider a stream in computer science? What would be a flow of data that you have to compute eventually? Anyone would like to take a stab at that? YouTube video, right? The data that come from the video, in many cases, it will keep coming, right? Another more closer to your own computer example is basically the way you handle opening a file, right? You open a file, uh, you basically say, hey, I want to read the file. What happened next? How do you actually process the file? You buffer, right? That's a great answer to that. Basically, the way you process a file, first of all, you say, hey, I want to open this file, and you put in the file name. Then, when you are ready to say, hey, I want to read the first line, you say fread, right? You do scanf in C. Basically, there'll be a function call in every programming language. There'll be a function call that deal with how do I open the content of the file and how do I read them, right? So you read them whenever you need to read it. Anyone want to take a guess on why don't I just read an entire file at the same time? Sometimes it can be too large, right? Think about it this way. Let me give you one example. Let's say I want to somehow run Google Map, right? Anyone want to take a guess how big is that map that Google has to maintain? It's quite big, right? So at the end of the day, you basically you need to make sure you manipulate the data in such a way that you only ask for what you need to process, right? So the concept of stream can come in. Basically, the definition is infinite, or in the case that we just discussed, it's too big. It's just way too big for you to buffer them all, right? By the way, when I said buffer, it means that I'm gonna store them temporarily somewhere, right, in the memory. Basically, I'm gonna have some temporarily variable, temporarily array to store these data. Uh, but the concept of stream is infinite amount of data coming in. Why is that interesting? Because many things rely on using stream, right? Data in real world, for example, is a stream. It's too big for your memory, be too big for your DRAM. Think of the size of the data center storage versus your own storage, your own hard drive and SSD versus the main memory. The memory that you buy when you buy DRAM, that's typically up to 16, 32 gigabyte, right? 64 gigabyte if you have a fancy machine, or maybe hundreds and hundreds of gigabyte if you own a cluster. And this concept of stream, you might see this as like, oh, is it big data? Yes, one of the things that you have to manage when you consider big data. It's a really old topic, right? Whenever someone said big data, it basically means that the data that are too big for the memory to handle. It's always been there. Back in the day, your memory is megabytes inside, right? Oh, back in when I was like a middle school student, that's a long time ago. Uh, we have megabytes of RAM, right? This day you have gigabyte of RAM. It's never enough. It's never going to be enough, right? Because you're gonna have more and more data. And here are some of the example of stream. For example, if I say a sequence of prime, is that an finite or infinite number? It's going to be infinite, right? Basically, 2, 3, 5, 7, 11, 13, 17, and I get slower to make sure that, hey, the number I just spit out is a prime, right? 17, 19, 23, 29, right? And it gets slower and slower. So let's say I'm at prime number that are greater than 1 million. For example, your exam, right? Your midterm, I ask you to implement a sequence a prime number. Is it slower if I ask you to do the number between 1 million to 2 millions versus the number from 0 to 100? Which one are going to be slower? 1 million to 2 million, right? Because you have to think a lot before you can spit out the next number, right? Because there's so many things that you can divide the number you're checking with. So one of the beauty of using this as a stream is, well, unless I say I need that prime that are greater than 2 million, do you need to start the computation right now? Sometimes I might not even need it, right? So that's when we think about lazily evaluate things. I'm going to show you a few more examples of stream. The other one is the digits that are used to represent pi, right? I can go to 3.1415. I don't even know what's the rest, but is it infinite or is it finite? Another infinite sequence of number, right? Or at least I think it's been proven to be infinite. I think I might be wrong. I'm not the mathematician. I'm not the physicist, so I might be wrong, by the way. Another example is, let's say you connect your LAN cable to a computer, right? The packet just comes in. It listens to, basically it's gonna keep listening to whatever comes in, right? The network interface card, or sometimes we call it NIC, right? Your internet card would keep reading the packet that's coming in. Do you know, is that finite or infinite? It behave in both way, right? Because basically, if you think about it, you only get the receiving packet when your computer requests something, right? It's up to the user behavior. But if I send a request, I might or might not get the sequence of data, right? But the way this is handled, because it deals with network interface, computer would treat it in a similar fashion as a stream. To access a stream, so basically the next concept, okay, I know what a stream is now. Any questions about like the definition of stream? I guess the formal definition versus the what are the things I use, and I'm going to represent it as a stream. So the formal definition is an infinite sequence of data. A more practical thing that we use stream for is anything that you know is going to have a lot of incoming data and you don't know when that's going to end, right? And to access that, how do you access a content in the file? So if I read the file, what will I get? What would be the first item that I'm going to get from that read function? I do fread, I do fscanf. I just want to read something from a file. Which part of the file would come first? The top line, right? Basically the front, right? The front of the content of the file would spit out first. And what happened if I read it again? You get the next thing, right? The next line, then the next line, then the next line. What does that look like? Are there certain type of data structure that you are familiar with? That looks kind of like that. You get the front and you get the next item, you get the next line. Yeah, it's a list of lines, right? So let's actually define a stream as type A, append with the stream of type A, right? Any question about this? By the way, this looks almost similar like a linked list. The only difference is you don't know when it ends. You don't know when it ends. And the formal definition is it never ends, right? But it's behaved like a linked list, right? Are you all in agreement that, hey, this particular definition looks like a linked list? The only exception is this one doesn't end. Then we can do pattern matching, right? Because we have a linked list. So we do the same thing. Let's pattern matching. We have a head and a tail, right? Any questions so far? Basically, just behave like a linked list. I can get the head, I can get the tail. By the way, this is back in Scala, not in Rust. So what was the problem here? First, as I said, this is infinite, right? So where do we start, right? Unless I recover from the beginning to nil, I mean, say we cover the beginning with nil. Where do we end? Because this is actually infinite sequence thing, right? So let me ask the last bullet line. Does the evaluation ever terminate? Can I get to the finish line when I open a stream? No, right? It doesn't really terminate. Uh, the way you handle files, I know that at the end of the day, you're gonna reach the last line of the file. So that's, as I said, that's why I said it's a practical use of stream. At the end of the day, you're gonna reach the last line. Conceptually, we are going to think about it as it's something that will keep coming and coming and coming, right? So remember our old friend, the double colon thing here? This operator is called the cons operator, right? The two columns. Uh, list is a recursive data type. You can append things at the end indefinitely. Keep putting things in, right? So this operator is actually created and it allows you to deal with stream because what does it mean when I say const a extreme extend stream say? What does it mean? When I say const extend stream? It inherit, yes, it does inherit the properties of stream, which means that it's gonna work on stream, right? So the const operator in Scala is available here if you're curious. Feel free to check the link. But let's think about, okay, what are the problems with, let's say, if I want to apply a function to a stream, right? Let's say if I want to do a map on my stream. How can I know? Because it doesn't end, right? Let's say I want to apply a function f to our stream. Can we use a map? Can I use a map? Yeah. So the first question is, can I use a map? I guess theoretically I can try to apply the map, but will that terminate? No, right? Because the reason is map by definition in Scala is an eager operation. Eager operation is, think about this. Eager operation is like that student who, whenever I got the assignment, I'll do it right away. I'll finish it right away, right? So what will happen if I pair that students up with an assignment that keep coming? It never ends, right? It never is going to end. That student will keep having to keep doing the assignment, and the assignment never ends, so he'll keep working. By the way, have nothing to do with the real life student, right? I'm not gonna do that. I'm not an asshole. Uh, I just want to make sure I put that analogy out to make sure it's clear. So what would be the solution here? We can be lazy, right? You take one element at a time and don't evaluate the entire thing, right? This is my life. I keep getting more things to do, right? And then this is basically everyone's life, right? Can you tell me? This might be a small philosophical question, but can you define the number of work you're gonna have to do in life? Is that by theoretically, is that infinite or finite thing? It's kind of technically infinite, right? Until you can't work anymore, right? So you're gonna, what are you gonna do? You pick the work with the earliest deadline, right? So I'm not gonna say that being lazy, but it's being smart. Like you know that this is gonna have more work coming in, so you deal with it the way you can handle that to make sure it eventually would finish the evaluation, right? So that's basically my analogy. Let's say you're gonna have infinite amount of work in life, so you do one piece of work at a time. You apply the function to the front of the queue, then to the next item, to the next item, right? So here is the naive solution to lazy evaluation. So let's say we want to evaluate just up to where you need, right? So let's say I use these two example. I want to get a pi digit up to digit number 5. So in that case, I'm going to return 3.1415 and then I'll stop my computation, right? I say, hey, that's good enough. You're not going to need the rest of the number, so here you go. I want to get the first 10 primes, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, right? You get the first 10 primes and you stop, right? So with this naive solution, what if? What if I say, hey, how about you get me the first 20 primes? And then in the next hour, I say, hey, can you get me the first 15 primes? What would be the downside of this? Basically, this approach. You repeat the calculation, right? So one of you guys send me a private chat that is it basically repeating calculation? And the answer is yes, you're gonna have to repeat it all the time, right? So that's bad, right? That's why I said this is a naive solution. The downside is, well, you have to do the same computation again. Right? Anyone here take DSOP and algorithm before? Are you familiar with the concept of memorization? Anyone not familiar with the concept of memorization? Okay, so if you're not familiar with the concept of memorization, I can explain it to you with our old friend Fibonacci, right? Remember Fibonacci function, and I told you it's a pain to kind of calculate Fibonacci at a high number? Yes, no? So what would be the easier way to do this? Can I solve it with loop? Store that in an array, right? So basically you start with what? You start at the first item, right? I do fib of 0. What is fib of 0? 1, right? And then fib of 1 is fib of 0 is 0. Fib of 1 is 1. Fib of 2 is 1. Fib of 3 is 2. Fib 4 is 3. Fib of 5 is 5, right? So you're gonna get 5, 8, 13, blah, blah, blah. So now that I have this array, and let's say I compute out to fib of 100. Okay. Let's say I have this computation of up to fib of 100. If I want to get fib of 88, do I have to redo the calculation? Or can I just go to the 88th item in my array? You can just go there because you already have that calculation. So one way you can do this is to buffer the 80th item, right? You cache the previous results. By the way, the term caching is to store things you computed, store data that you have actually fetched and accessed before. So this concept is called memorization. And lazy evaluation basically is doing as minimal amount of work as possible to get your goal. Sometimes we call this either call by name or call by value, call by need, right? So let's say we have two functions, f1 and f2, and we want to evaluate f1 or f2, right? So what if, right? What if I know that f1 is true? Do I need to call f2 at all? No, right? So if you need to evaluate f1, I know that f1 is true. I can lazily evaluate by not even having to compute F2. I know that's true, right? So being lazy can also mean being smart. Right? It's a good thing. Uh, any questions so far before I move on to how do we do this in Scala? So in Scala, you can use the keyword lazy, right? It's as simple as this. Let's say I have an array that consists of a list of 1, 2, 3, 4, 5 to, I think, what is this? 10 million, right? 1 to 10 million. I do temp2 equal temp1 dot map. And this is basically doing what? It's power of 2, right? So you do a power of 2 of everything in temp1. That would take some time, right? So I'm going to do a lot of things and then I say print temp2. So from this example, because I specifically said, do this thing lazily, when will temp2 get evaluated? When that's being called, which is right here, right? Traditionally, you are actually going to evaluate here unless you put in the keyword lazy, right? Unless you put in the keyword lazy, it's going to get evaluated right away. In this case, it get evaluated later. So can anyone think of what would be the benefit of this? What could be the benefit of this? So what if first of all, the code before that line would get run right away, right? You don't have to wait for the temp2 calculation. But let me say this. What if before here I have if else? So when will I need to get the print line temp2 things to run? It's only if the condition in the if statement becomes true, right? No, don't restart the window, my bad. Okay, remind me tomorrow. Sorry, my machine is trying to update itself. So if this thing is true, do I have to calculate temp2 if this thing is true? By thing, I mean this. Yes, right? What if it's false? You skip, right? So it's the beauty of lazy evaluation. You can skip things. Sometimes it does happen, right? Sometimes it does happen. So make sure you know that this is a concept. The concept of lazy evaluation is I'm gonna calculate whenever I need it. That's a great question. The question is then why don't I just define temp2 inside the if statement, right? For this particular example, it's possible, right? Sometime, what if you need to use temp2 somewhere else? So what if you have this if, right? Use temp2, else if you use temp2 again. And then else, you don't need temp2. Right? In this case, you need to make sure the scope would cover the first two if else, but not the last one. Right? So in this case, it's much easier to put lazy evaluation up here. All right. Okay, so let's move on to the next concept called dunk, or sometimes we call it Jensen's device, right? What is it? It's basically a value that's not yet evaluated, right? But when you call it, you return a value as if you have evaluated that. And a dunk is going to be evaluated lazily, right? Think of it as I'm going to delay the evaluation as soon as possible, right? I call a function. I'm going to return it, but that return value has not been evaluated. With me so far, basically this work lazily. I'm going to return something. I haven't computed yet, you can use it. If you need to use it, that's when you evaluate that. You can delay the evaluation. The information needed by Dunk is what, right? So if you call a function, what do you need as an input? Is here in the bullet point. You put in the input arguments, right, to your function, f of 1, f of 2, basically, right? This is your argument. You need to put it in, and you also need the environment at the time of call so that you can actually apply the function. F of this will be lazily evaluated with the concept of a dunk, right? So the next question, okay, sounds nice. How do I implement it, right? So let's say you have a function that returns a. Generally, you need this. If a value is already calculated and the result is v, you are going to return v, right? This is the obvious part. I got result, I'm going to return it. Otherwise, I'm going to evaluate the expression. Switch back to Rust. You can use dunk lazily in Rust. There's a API support called dunk. So it's already been implemented. To use it, this function, if it's already been calculated, you're going to get a value. If you haven't been evaluated that particular expression and you need to use it, then it gets evaluated and you can use it in Rust. Right? Any questions so far? Okay, so let's move on to another concept. Well, the same concept again, but you remember call by name? Can someone tell me what's call by name? I think lecture 2. You substitute first, right? You do the substitution until at the end, right? And then you evaluate it. So at this point, you might be asking, clear, so what's the difference? Call by name is when you evaluate, right? Evaluate the expression only when needed. So the downside is you need to call 5 times. You still have to repeat the execution, right? With lazy evaluation, through the concept of dunk, right? Through the concept of dunk would apply memoization. Right? So it's going to be faster typically than CBN, right? And CBN terminate even only if our lazy evaluation terminate. So what would be the downside of this? Can someone tell me what is the downside of using dunk in this case? It's going to remember the calculation you did earlier, right? Keyword is you have to remember the calculation you did earlier. So what's the downside? Versus I'm going to redo the calculation again. It uses up memory, right? It uses up memory. So it take more space. We call this, it use a lot more, it can use more memory footprint, right? Memory footprint. So there's a trade-off between compute power. If I know my processor is really fast, right? Recompute may be fine. Don't waste the memory. Right, so it's a trade-off between compute and memory, and you have to somehow think about, okay, do I use dunk or do I use just CBN? Because dunk would require some memory, right? But it's fast. It's fast. It's going to be faster than CBN in most cases. Okay, so now we would switch back to our in-class exercise. Well, toward the end of the class, I think we have a lot more time left, so I'm going to cover the rest of the material first before we switch to in-class exercise 12, right? Both will be in Scala. Do 2 things. Implement all prime after and using lazy evaluation. Remember the keyword lazy. Make sure you use that keyword lazy. Implement factorial up to n, also using lazy evaluation. right? And when you want to test it, just call the function to get the factorial. Any questions about the in-class exercise? Because if not, I'm gonna do a quick break. And by the way, this part, if we're gonna switch to Python, because it's just a concept of iterator versus generator, uh, we'll switch gear a little bit. So we'll do actually we have quite a lot of time. So let's do an 8 minutes break. We'll meet again at 12:50. Is that okay? All right, awesome. So I'm gonna pause the recording. Okay, so let's resume the lecture part into the concept of iterator and generator, right? So let me ask you this: what is an iterator? What are the key properties of iterator? It has the next element, right? And you can actually get the next element. So this gives you basically an illusion of a linear sequence, right? It's something that allows you to traverse collection of items, right? Imagine how bad the world can be if you cannot get an iterator. You have a set and you don't know how to go through your set. You have a map, but you don't know how to go through your map. You have a list, but you can't go through your list, right? Uh, the interface is pretty simple, actually. As we just said, actually, it's like 2 minutes ago. Sorry, I don't know why I said a lot of the word, actually. Uh, Based on what we just developed, right? There are two things that you have to implement to get a functioning iterator. Do I have the next item? And what is my next item, right? And this notion of iterator comes in many, many, many languages. So that's why we use Python, because it's simple, right? So iterator in Python, how does it work? If you have iterable object, right? Object that can be used with a for loop, there's gonna be a way for you to get the next element. And there has to be a way for you to determine if there's no more elements, right? So let's create that. In Python, you can use iter or the iterable object, right, to get an iterator. What will happen if I do this? If I run this, will there be any problem? It's out of bound, right? You're trying to get 4 things out of your collection that only have 3 things. Iterator cannot magically come up with a new item out of the fly, right? Out of the blue, by that, because it doesn't know what I'm gonna do next. It doesn't even have the next item. So what are the other interesting thing about iterator? When you go through each item, how many times exactly do you visit each of the item in your collection? One, right? You go to them once and that's all. So with this concept of iterator, let's build one from scratch. Right? Let's build one from scratch. What would be the requirements? So fundamentally, this is what we need, right? We need like one internal index. Think of it as a pointer to the current elements, right? Think of it as a pointer to the current elements. You also need one internal way to keep track of the number of elements, right? Why is that the case? Because you need to know how many you have left, right? You need to know how to count how many have I been through, and you also need to know how many do you have left. So there are 2 methods. One is a method that would return an iterator. Another is a method that would return the current elements and move the index to the next elements, right? So in Python, you can use a constructor for sure, right? But let's kind of let's formalize this and build it. Right? Not formalize it, but concretely build this. Right? Let's build the iterator from scratch in Python, by the way. So are you all have been using Python before, by the way? Because this is a lot easier. Okay, awesome. So let's build one from scratch. A constructor is going to be something like this. When I init, when I create an iterator, how many items would be in that iterator? In this case, basically I build a constructor that takes n as an input, right? So what I can have is an iterator that has n items. I also need a method to return the actual iterator itself, right? So if I init, I have my own. Basically, this is like built in so that I can return iterator. And then the next element, right? The next element you have to build in is next. No pun intended. I'm sorry. But when I do this, so let's say I do itr.next, what am I supposed to do? In Python, I just call next. What am I supposed to do? Yes, exactly. So I'm gonna first check if do I have the next item, right? So that's the first thing. Do I have the next item? If I do have the next item, I can iterate. When I can iterate, I will say index equals self.index so that I can return, right? So I can return index, which is basically the current item. And then I increment self.index. I return the next, the current elements, and I move on to the next elements. Otherwise, I would do this. Raise stop iteration, basically say, hey, I don't have any more. Dang, I'm stopped. And here are some sample usage, right? This is super common. You use it in conjunction with the for loop, right? You can do num in range 5. What will this do? What will get print here? You would print 0, 1, 2, 3, 4. You iterate inside the collection that is generated by the function called myRange5, right? So you're gonna start with 0 up to 4. You can use it in conjunction with the list. You can say print list myRange4. Basically, this would create first the iterator that go to the list, and you can print each item out, right? You can use it manually. You can say it equal iter, right? Iter in Python would create an iterator, myRange2, and then you can say print next, right? This would give you the number 0 and then 1. All right. So what is the overhead of of creating and working with iterator? So what are the main things that you have to do to maintain iterator? It's already been covered in the past few slides, actually. So what do we need to keep track? You keep the index, right? And you need to write certain specific methods to deal with the index and how do I increment it, right? So another concept, anyone here heard about the word generator? Okay, I will take long pause as a no, so this is great. Generator is kind of tied to the concept of stream a little bit in the sense that what if I want to ask you to keep generating elements? Can I use iterator for that? Can I use iterator for infinite things? Not exactly, right? So what's the overview? So let me give you an overview of the generator first. So let's say I have this. What's the type of the following expression? I'm gonna apply square, right, for every x in these elements. It's a list, right? It produces many values in this sequential order, not on sequential, right? It produces the list in sequential order. So in programming, I'm gonna compare that to a function. A function produces one value as an output. For multiple output, you apply multiple function calls, right? For a generator, it doesn't require multiple function call. So if I'm gonna go back one slide, I'm sorry about that. I'm gonna go back one slide into this example. If I want to apply this and use generator, I have a control. I have a control over when I'm gonna compute x squared. And that's why we tie this to the lazy evaluation and stream, right? I have a control over when I'm gonna do the 3 square, right? When I'm gonna compute the 4 square, when I'm gonna compute 1 square, when I'm gonna compute 2 square. And generator give you that control. And I'm gonna tell you how. Basically, this is comparison against a function. If I have to do that particular function call, I have to apply the multiplication on every single element, which by the way doesn't really work on an infinite elements, right? But with generator, you actually would call the generator, you get an iterator object and you go one by one. Basically, you go one by one, similar to the iterator, but you apply the function, right? Iter and next are implemented automatically. And you can yield. You can yield. What does yield mean? Yield basically means that I'm gonna stop. Iterator, don't go forward. Stop. I would stop. You can resume whenever you want. You can stop whenever you want. It's similar to when you have to apply a map, but you have the play and pause button, right? Would that be great if I have a map and I have a play and pause button? Same concept, right? Everything is stored when you pause, so you can resume later. You can pause and resume. All right. Any questions so far? So this works like an iterator, but you can stop in the middle and stop computing whatever you have to compute. So think of generator as iterator that can apply function call. Right? Iterator that can apply function call. Give me one second. Sorry. My in-laws are at in the hospital, so I want to double check. Yeah, okay. So once you pause, you can have the control to resume, right? And when you are done, similar to iterator, you have stop iteration that is raised automatically. So you can hand off any internal state, basically using the concept of iterator, using what we call coroutine, right? Coroutine can be used in conjunction with the iterator. No, my bad, with the generator. So generator can pass the internal state in the background, similar to coroutine. So I'm gonna use an example to make it more clear. So I'm gonna go through an example and explain through the example. And here's the example. Let's assume I have the following iterator. It's a function call, right? Generator, as I said, is a function, but you can call and it would yield. You can say next, right? So when I have this generator, so this is a generator. And let's say I call this generator G. Let me name it G, right? What will happen if I call next G? Anyone wanted to guess if I call next G in Python, what will get print? So first of all, it would run, right? It would run. So it's gonna print full A. What will that return? Yield, it means that I'm gonna stop and return this. It returns 3, right? So what will get print overall? you get foo A, right? And you get 3 as a return value. Well, it didn't get print because I didn't say print next G, right? But you get the idea. What if I call it again? Next G. What will I print and what do I return? In this case, I'm going to print foo B, right? Basically, I continue and I'm going to return 5, right? So, is it more clear now that, hey, you can use a generator by this method? And the beauty of this is, what can I do to get the list of prime number up to any number I want to, from 1 to any number? How can I do that? So let's assume I have a function called is prime implemented, right? Is prime n, right? I can do this. Foo 2, right? I'm gonna loop from 1 to infinity. I just keep incrementing, right? Yeah, pretty much. So there's a chat that says keep the list prime and compute from that num. So I'm gonna loop from 1 to infinity, and I'm gonna do this. If is prime, and let's put this number as m, right? If is prime m, yield m, else m plus plus. Basically, keep looping. That's it, right? So what will I get when I call next foo2? What will return if I say next foo2? The first one, basically. The first time I call this. It starts from 1, right? So this first we will return 2. If I call it again, next foo of 2, what will I get? 3, right? If I call it again, I'm gonna get 5. If I call it again, I'm gonna get 7, right? Because it's gonna basically resume that loop. Anyone want to take a guess of what's the benefit here? First of all, you don't have to repeat the calculation. Second of all, if I need a huge prime number, I call the function, I got one number, I'm done. I don't have to wait for the second number, third number, fourth number. I have a tool that allow me to generate the next prime number, basically, right? So from this example that do foo A, foo B, foo C, right? You can do something like this. And I encourage you to try this in Python because first of all, this thing would give you foo done, right? And double check here what would happen if I call h equal foo and print the list. So this is like a mini in-class exercise. Try it out and see if you get the stop iteration or do you get foo A, foo B, and foo C and foo done. When I have edge that takes up foo again. All right. So with this, you can use generator for infinite sequence. And because we start with scalar in the beginning part of the lecture when we talk about lazy evaluation. Right now, I'm gonna transition into, hey, we can apply the same concept in Python, right? So that you can see that conceptually, whatever we learn in Scala is a property of language. It's a property of a language. And you can apply this property across different languages too. It just depends on how you want to implement it. So let's say you want to get the next prime in a code routine, right? Finding the next prime is computationally expensive. Why? Again, repeat calculation. Pretty much, right? You have to go through a lot of number. So we want to limit how many prime number we're gonna produce because that function call will be long. So generator can address this problem as we discussed earlier. Value would be yield back and you pause the computation so that you don't have to compute the actual infinite sequence, right? And the generator allow you to keep producing the next element, right? Anyone here, I'm sure everyone here has Netflix, right? Right? Yes, no? Yeah, Netflix. Well, if you don't have Netflix, it's basically is a service where you can watch a movie, right? And I one of the thing I like the newer version of Netflix, if you kind of hover around like, should I watch this? And you move through movie, what will happen? What will Netflix show you for the current movie that you're reading that, hey, this is a movie about something? On top of just a synopsis of the movie, what does Netflix do these days? They're gonna show the trailer, right? And in some cases, if you hit the play button, what will happen? Well, actually, I think there are some. It's not the trailer anymore, but if you browse through Netflix, I think it at least on my TV Netflix app, what will happen is instead of showing the trailer, it begins. Yes, if you watch like a show, a series, right? It won't just show the trailer; it's actually show the episode. So it shows the beginning of that episode, and you have a choice of, okay, this looks boring. I'm gonna pass on, right? You stop, move on to the next series so that hopefully you can find something to binge watch, right? Think of it that way. Completing the entire episode to figure out if this is boring or not, it's gonna take a long time, right? Typically, one episode is between 25 to 40 minutes. It can go up to 2 hours, right? But you have the option to pause, move on. Generator conceptually, I guess that's my analogy for a generator, right? No, we're not doing that, by the way. We have the in-class exercise for lazy evaluation, so we will not. But if you are curious, try to do what I just wrote earlier. In Python, write a function that generate a list of prime where you're gonna keep yield the next number for prime. You can use recursion on generator, combine topics that we learned, recursion and lazy evaluation. Generator can be used recursively. For example, if you have a nested list. What is a nested list? It's a list of lists, right? It's lists inside the list. So if you need to actually go through everything in the list of lists, you can use generator too, so that you don't have to go through everything. You don't have to go to everything at once. You just need to go through each item, right? So this is basically implementation. The way it works is it keep going through the first list. Then you keep going through the next list. Then you keep going through the next list, and that's all, right? Uh, you can also pipeline a generator, right? So what does pipelining mean? Pipelining basically means that I'm gonna hand off my results to the next worker, right? Uh, how should I do this? Have anyone watched like a cooking show before that you have like a line shelf and then you have the head shelf and you have like multiple shelf that would like do multiple things to finish a plate? Anyone watch those? Yeah. So basically in in a fancy restaurant, right? One of the things that happen is each cook will do certain things. And how do they put together a plate before it gets served on your table? Can someone tell me how does the head chef organize everything. Yeah, it's kind of like type in C. You separate the task, right? You separate the task, and once the first guy, let's say I need to grill the meat, right? I'm gonna grill the meat, and I'm gonna hand off this grilled meat to the next person, who would then plate it. He or she would then take, let's assume this grilled vegetable with some mashed potato, right? So they'll scoop up a mashed potato which is processed by someone else, right? And along with some vegetable, move it to the next person. They might be pouring some gravy on the mashed potato. Move it to the next person. Garnish the dish, right? Before they look beautiful, so they can display it on your table, right? So that's pipelining. One person do some certain amount of task, move it to the next person. Perform the task, move it to the next person, right? So you can use generator for that too. Generator can be used to pipeline a series of operation, right? You can pipeline a series of operation. For example, let's say I run a pizza restaurant, right? I want to get the number of pizzas sold per hour from the log of sales, right? So I can do this. I can run the code, and I can actually, instead of processing everything all at once, instead of processing everything all at once, I can cut it based on, say, days, by basically rewriting this code to use the generators to process each day sales log, right? So that's actually it for today's class, because it's kind of like, I think it's a new concept for many of you, like things like lazy evaluation. We will basically focus on in-class exercise here, right? So we're gonna move to Discord. We'll go through the in-class exercise together. I'm gonna be on Discord in about 7 minutes. Is that okay? All right, awesome. So that's it for today's lecture portion of the class. We'll be in on Discord in about 5 to 7 minutes at around 1:30. All right. Let me stop the recording.